Hello everyone, my name is Liviu Popescu. I am from University Polytechnic of Bucharest, and I will be presenting you the paper Control Analysis of a B-motor electric traction system for energy and performance optimization. Before starting the presentation, let me introduce some objectives of our research. And we know today that an electric vehicle are more and more attractive in a solution with multiple motors. Why? Because there is an opportunity to reduce the size of each motor and to approach the mechanical, the production of the mechanical power to the wheels, and provide energy and performance optimization to the vehicle. One of the objectives of the study was to cover the operational area of an electric vehicle, how to cover this operational area. Secondly, how each motor contributes to the electric traction system, and in our case, it's a system with two motors. And of course, how to optimize and how to improve the energy efficiency in such system, of course, preserving the vehicle stability. Some main items, main topics of the presentation. As we talked before, the operating points will be the first topic, how to calculate the operating points for the vehicle and respectively from the for the powertrain. The electric traction system, in our case, with two motors, two brushless DC motors. The identification of opportunities for optimization in using the losses reduction for the B-motor solution, and some scenarios studied in this research for the torque allocation between the two electric motors. Before presenting the simulation and the results of this simulation, it's important to specify that input data for our study, we used WLTC testing cycle, so a normalized testing cycle. I can specify that in the study it was integrated a light vehicle. So this is an appropriate testing cycle for that. And from this we have the speed evolution for different moment of time during the period of the testing cycle. From this speed, we are able to calculate, of course, the acceleration and force attractive effort to be developed by the powertrain. From the vehicle characteristic, we are able also to make this this calculation. So we know the attractive effort for such a vehicle is composed by many forces, so many resistant forces. First of all, we have the aerodynamic drag force, dependent of the frontal surface of the vehicle, of the air density, of course, the square of the speed, and also a coefficient, the aerodynamic coefficient of the vehicle. The rolling resistant force, and of course the grating resistance force when the vehicle has to go on a up or down on a slope, and when we have to accelerate or to decelerate the vehicle, we have to take that into account. So we need the mass and the acceleration or deceleration requested for the vehicle. Using this attractive effort, we are able to specify a map of the attractive effort distribution for each speed request, taking into account the data, the input data, the WLTC testing cycle. Of course, it is possible to specify not only the tractive effort but also the torque. And in order to choose the motors, we suppose on the motor's characteristics the torque. The operating points regarding the torque request. In our case, two brushless DC motors, we can see that each motor can answer the request in terms of the torque but we have a second request regarding the vehicle. So the vehicle has to climb a slope angle of 15 degrees, and in this case, one motor is not enough, and we have to use the two motors. Before going to the optimization process, some information regarding the power lost in the motors. So considering that the power loss is composed by two items, the iron losses and the Joule losses. The Joule losses are dependent on the internal resistance, electric resistance of the motors, and also the current passing through the motors. And considering the iron losses dependent on the hysteresis losses and the eddy current losses, we can specify for these iron losses that they are dependent on the speed and the square speed of the vehicle using some coefficients, respectively the KH, the hysteresis loss coefficient, and KF, the eddy current loss coefficient. N is the motor speed. We used two scenarios for our study. The first one concerns the total losses optimization, and the second one it's something between performance and optimization. So we tried to use both motors, and for acceleration phases, the motor one, the rear motor, had more involvement than the first motor, so 60% of the torque covered by this motor. And for the constant speed phases, it was used more the front motor, so the motor motor 2. The results are important. So for the situation without grading resistance, so on a flat surface, after the WLTC testing cycle, we obtain 85.7% energy efficiency for S1 and 85.5% for S2, and an increased result, so a better result for the situation when the vehicle had to climb 15 degrees. So 90.2% for S1 and 89.5% for S2. In order to understand better this result, let's see the total lost energy versus the mechanical energy produced and the iron losses. And in the case with without grading resistance, so the test on a flat surface, we can see that Joule losses are reduced. They are maybe more important in more important in the situation with grading resistance, and this is for our cases a situation when it's more place for optimization, as you also saw from the results obtained by the simulation. Also, to sustain that, we have here the joule losses distribution between the two motors, depending on the currents passing through each motor. So from each point, we can have the influence of each motor to this total joule losses distribution. As a conclusion, we know that today the electric motors are more and more performant, but even in these cases, in the situation with a solution with multiple motors, there is still place to optimization, and so it's still possible to optimize in a multi-motor solution. Secondly, as we saw on the results obtained during the present study, the optimization process is more effective for increased tractive efforts. And of course, the optimization is a compromise. Why it is a compromise? Because anytime we have to put in balance the performance of the vehicle, but also the energy consumption. And first, before that, the vehicle stability is a must. So we have to preserve the vehicle stability. I would like to thank you very much for your attention, and I will be waiting for your questions. Thank you very much.